Now we're going to look at how we create confidence intervals. And the first one we're going to do is how to create a confidence interval for a population mean. Creating a confidence interval requires that we calculate this t-multiple that we had called before, and the standard error for the sample mean, as well as understanding our desired confidence level. The confidence level is the desired confidence required for the population mean to lie within. So for example, we want a 95% confidence level or a 90% confidence level. Our formula is given by the following. It's the x bar, which is our sample mean, plus or minus the t-multiple times the standard error of the sample mean. So again, if you recall from before, we had our graph that showed our point estimate, which is in this case, it's the sample mean, which is x bar, and then the upper bound and lower bound is going to be created by this t-multiple times the standard error of the sample mean. Now remember that our standard error can be replaced by the following. The sample standard deviation divided by the square root of n, which is the number of observations. Our t-values, the t-multiple, is calculated in Excel using the t.inv.2t function for two-tailed. Since we're looking for a confidence interval that is above and below the mean, we're going to have a two-tailed probability, the probability of it being in the upper tail or the lower tail. Since the confidence level is 95%, we're looking for the probability of 1 minus 95%, or 5% in the two tails. And we're going to use that for the Excel function. So therefore, we would use the following. t.inv.2t for the two-tail with a 0.05 area and the number of degrees of freedom. So let's take a look and see how this works. Let's say on the right we have this data set which has 50 test scores. We're only showing 20, however. We calculate the mean and standard deviation, and we know how to do that using the average and standard deviation.s function. We'll calculate the standard error, and we're going to use the given confidence level of 95%. Now, we'll do the t-multiple first. And so we said that since our confidence level is 95%, we are looking for the area under 5% of the curve at two tails. So it's going to be 0.025 on one side and 0.025 on the other, giving us 5%. And since the total test scores is 50, we're going to use the degrees of freedom of 49, n minus 1. So remember that the standard error is the sample standard deviation divided by the square root of n. So this is going to give us the following. 84.38, which is our x bar, plus or minus the t-multiple that we had calculated, which is 2.010, using the Excel function. And then we multiply that piece by 9.899, which is the standard deviation, divided by the square root of 50. And this will give us the confidence interval of 81.57 to 87.19. So remember that our x bar was 84.38, and it lies in the middle of this. So it gives us the range of a lower bound of 81.57 and an upper bound of 87.19. Now, not all confidence intervals are going to be based on a mean. We can also create a confidence interval for a total. Now, it's a little bit less intuitive, but let's say we're trying to determine our total revenue for all customer accounts. So T represents the population total for estimation, and the T with the little hat over it represents our point estimate for the total. And what we're basically saying is that if we knew individual accounts and we had a sample of the accounts, and we knew that our entire population of customers was, say, 100,000 or a million, we could calculate an estimate for the total and get a confidence interval for that total. So our point estimate for the total is basically given by this t hat, which is equivalent, we'll do the right side because it's a little bit easier, the total population times our sample mean. Thus, our expected value for t hat is going to equal t. So our expected value of the point estimate should be the actual total. Our standard error for the t hat, for that estimate, is going to be equal to n, which is our total observations, divided times the population standard deviation divided by the square root of n. So we can therefore estimate this by fixing the standard error of the t hat to equal n times our standard error of the sample mean. And thus we have the following confidence interval. T hat plus or minus the t-multiple times the standard error of the predicted total. So let's take a look at an example for this. From the data set on the right, we have 100 samples of our customer revenue accounts, but we only show 17. We calculate our mean and standard deviation, which you can see on the right is 2601, and the standard deviation of 1430. We also have calculated the standard error and the t-multiple in the yellow box. And we include a total estimate, which is our t-hat for the total estimate, which is equal to the total number of observations times our average sample, where n is the total population. So therefore, we have our t-hat plus or minus the t-multiple times the standard error of that t-hat estimate. Again, our t-multiple was calculated using the t.inv.2t function for the two tails. We use 0.05 because it's a 95% confidence interval, so we do 1 minus 95%, giving us 0.05. We have 100 samples of customer revenue accounts, so therefore we're going to take 1 minus that and get 99. So therefore, what we do is, in order to calculate it, at the bottom we have another set of boxes which says our total population size is going to be 10,000. So our total estimate is going to be our mean, which was 2601, times the 10,000, giving us 26 million. Our standard error total, which we calculated, is going to be 1430082. Now when we do this, we're going to create a 95% confidence interval for the total. So that's what is on the bottom. The 95% confidence interval in the yellow box would be the confidence interval for the mean itself, but we've extended this to include the total. And we end up with 26 million plus or minus 1.984, which is our t-multiple for this, times 1430082. And we'll end up with 23 million on one side and 28 million on the other side. Our 95% confidence interval will be between 23 million and 28 million. Now let's assume we want to check for a ratio or proportion. Now when would we do this? Well, we know that in news networks we always hear the 46% job approval of their senator or the president, or 56% approval. Well, this represents a ratio or proportion. So when we say 46% of the people approve of the job of their senator, the ratio is 46 over 54, which would be 46%. The point estimate for the target of the proportion is p hat, and the opposite is 1 minus p hat. So from above, our p hat is 0.46, and 1 minus p is 0.54. In order to calculate the confidence interval around this ratio, we're going to use an equation similar to the ones before. However, this time we're going to use a z-multiple instead of t. Now, the standard error of p hat is given by the following formula. It's the square root of p hat times 1 minus p over n. And this describes the error around our point estimate for the success proportion. Now, why are we using the z-value and not the t-value, since we had been talking about the variance before for the population, for the confidence interval around the population mean, and we switched to a t-value? Why are we switching back to a z-value? Well, let's look at the formulas for the standard error again and understand why this is occurring. Before, we had a standard error of the x bar, which is the sample mean, as s, which is the sample standard deviation, over the square root of n. Because remember, this population standard deviation wasn't known. And so therefore, we had an estimate. So this introduces a degree of variability. But the standard error for our proportion, our p hat, doesn't have that extra variability. On the left side, we have the variability of the mean, estimating the population mean, but we also have the estimate of the standard deviation, estimating the population standard deviation. We don't have that on this side. We really only have our one estimate, which is the p hat. So because of that, we don't need to use the t distribution. We're going to be going back to the z distribution. But remember, as the number of observations get large, the t distribution tends to normal anyway. So as the larger and larger number of observations, you wouldn't see that much of a difference whether you use the t distribution, a t multiple, or a z multiple. On the right, we had a survey of 500 people based on the president's approval rating. In this case, it was found to be 55%, 275 approve, 225 disapprove. So our sample size is 500. So the sample proportion is going to be 0.55. Now, if we want the confidence interval, we're going to choose the p hat plus z multiple times the standard error for p hat. The z multiple is calculated with the norm.s.inv function. Again, this is the standardized norm function. We put in the area of the curve 0.975, and you might say, well, why is it 0.975 when we want a 95% confidence interval? And that's because, again, for this function, we're using the two tails. There's no 2t function. So what we have to do is we're basically going to say that we're looking for 2.5% on each side. So what we need to know is the 0.975, and this gives us 1.96 as a result. So further, we have the SE of p hat is equal to the square root of p hat times 1 minus p hat over n from our formula, which is 0.55 times 0.45 divided by 500, and this gives us 0.022. We plug these values back into the formula, and we end up with 0.55 plus or minus 1.96 from our z multiple, which equals 0.5064, which equals 0.5064 for the lower bound and 0.59 for the upper bound. And we will interpret this as the president's approval rating was found to be 55%, and it could be as low as 50%, and it can be as high as 59%. So that's a key thing, because the margin of error is determined by the part of the equation after the plus or minus. It is the 1.96 times 0.022. So in this case, the answer for that is 0.0435, which we round to 4.4%. So we can say that our margin of error is 4.4%. Now, if we want to find a confidence interval for differences between means, this is a little bit different. Now, why would we do this? Well, let's say we're trying to compare two samples to see if the point estimate means are different. Well, in this case, we have two graphs here. We have a class A and class B. And we see that here's our confidence interval for class A, and here's our confidence interval for class B. And we know that the population parameter is going to have to sit between the confidence intervals. So if they overlap, then the population parameter is probably going to sit in that overlapping section. And we could see that between class A and class B. If they're from the same population, that's going to be true. But if they're from different populations, then that won't be true, and they will have different population parameters. And this is what tells us that the two samples probably come from different populations because their confidence intervals don't overlap. And this is what we're looking at when we're looking at the confidence interval for differences between means. And we'll get a little bit more in detail when we do tests for means. So here's what we look at it when we see the formula. It's pretty much similar to the other ones that we had. In this case, we have the first part, which is x1 bar minus x2 bar. So that's the sample mean of the first sample and the sample mean of the second sample. We do our plus minus, the t multiple, which we've known how to calculate, and we multiply that by the standard error of x1 bar minus x2 bar. Now this is a little bit different because the standard error x1 bar minus x2 bar is actually going to be the pooled estimate of the standard deviation times the square root of 1 over n1 plus 1 over n2. We have to combine the standard errors of both of the samples, and so it's done by a two-step formula. So we see here we have this SP, which is the pooled standard estimate, and it's a little bit of a long equation, so it's the square root of n1 minus 1, so the number of observations in sample 1 minus 1, times the square of the sample standard deviation, which is really the variance of the first sample, plus n2 minus 1, so the number of observations in sample 2 minus 1, times, again, the variance of the sample 2. And we divide that by the total number of observations, which is n1 plus n2, and we subtract 2. It's similar to the other one, and knowing the formula isn't as important as to why in an introductory statistics course, but would be a little bit later on. So let's take a look at an example here. On the right, we have 28 sample salaries, 20 are shown. The pink box shows the Excel calculations that were done for each of the samples, N1 and N2, Department A, Department B. And we calculate each mean, which is X bar, X1 bar, and X2 bar, and their differences, which is X1 bar 1 minus X bar 2. Now, from the previous slide, we saw that the confidence interval was given by X1 bar minus X2 bar, plus or minus the t multiple, times the standard error of the difference itself. The t-multiple is now calculated with n minus 2 degrees of freedom and a 95% confidence interval. So we're going to use, again, the equals t dot inv to give us the area under the curve of a t-distribution. We do the dot 2t for the two-tail, and we do 0.05 because we want 0.05 of the curve underneath those two tails. And so it's going to be comma 54 for the degrees of freedom. So there's a total of 56 observations, but now we're doing n minus 2 degrees of freedom, and that's because it's n minus 1 in each of the samples. So we're holding one for the first sample, we're holding another for the second sample, and that's why we're doing n minus 2. It's because of the number of samples. Our mean difference was calculated as x1 bar minus x2 bar, which is 8827. Our pooled standard estimate was now calculated as 32786. So therefore, the standard error of the difference is given by the following formula, which turns out to be 8762.57. Therefore, our confidence interval between the means is the 8827 plus or minus 2.005, which was calculated as the t-multiple, times 8763, which we rounded, which equals 8827 plus or minus 17.568. So our confidence interval for the difference between the means is negative 8740 and 26935. So you're going to notice that that span covers 0. In other words, it goes across 0. And so what that means is that the difference between the two means has a possibility of being 0. If the confidence interval did not cross the 0, it means that the two means, or the two samples, will be different from each other. And we'll see this in a little bit more detail in one of the future chapters. Now, we could do the same thing with proportions. So we want to see the difference between proportions. And we might do this in a way that says we have two samples where we have a number of successes and failures. If we're sampling, let's say, parts or that come off an assembly line, or yes-no responses, or approve or disapprove responses. So let's say we were trying to calculate whether or not one sample voters would say yes to a proposition or no to a proposition. We would take two samples and we want to see if the two samples are, what their confidence intervals are. Our formula is similar to what we had before. In both cases, both are from the proportion as well as the difference of the means. We see that we have the proportion 1 prediction point estimate minus the proportion 2 prediction estimate, plus or minus the z-multiple, again, as we had discussed before, times the standard error of the difference between the two. The difference between the proportions is calculated by the difference of success in sample 1 minus the difference in success for sample 2. So this is a difference from the x mean, or the sample means, but it's a similar concept. Our standard error for the difference between the proportions is a little bit different. This is going to be equal to the square root of the prediction of success for P1 for sample 1 times 1 minus P1 over N1. So you remember that this part looks like the way it was for a single proportion, a confidence interval for a single proportion. But now what we're going to do is we're going to add for the second sample the same thing. So the predicted success for sample 2, P2 hat, times 1 minus P2 hat over N2. And then we will take the square root. So here's our sample. From the data set on the right, we have 300 tests of products, success and fail. So did the items pass our test or fail our test? We have 2 trials, but we only show 20 here. So 1 means success, 0 means failure. We want to obtain a confidence interval between the difference proportions in the 2 trials. The success in trial 1 was 0.56 and the success in trial 2 was 0.64. Therefore, we have the following formula: P1 hat minus P2 hat plus or minus the z-multiple times the standard error of the P1 hat minus P2 hat. Again, we calculate our z-multiple using the norm.s.inv, 0.975, because again, it's a two-tailed test, so we need to divide this by 2 because we do not have a direct two-tailed test in Excel, and this will give us 1.96. So we have P1 hat minus P2 hat, which equals negative 0.08. So our standard error was now calculated as the square root of 0.56 times 0.44 divided by 300 plus 0.64 times 0.36 divided by 300, and this gives us a value of 0.04. So therefore, our confidence interval will be negative 0.08 plus or minus the 1.96 that was calculated from the z multiple times 0.04. And therefore, we have a lower bound of negative 0.002 and negative 0.158. You'll notice that this does not cross zero, and when the confidence interval does not cross zero in terms of the difference between the proportions, that is an indication that there is a difference between the two proportions. If it crossed zero, as we had said before with the means, it would mean that there was a probability that it was zero, and so they would be statistically equivalent. But in this case, because it doesn't cross zero, then that's not the case. We would say that these two samples are very different.